related to the fact that I'd like to, if possible, I'd like you guys to download an app for your phone. Used to be you couldn't assume everybody had a phone, but I'm kind of assuming everybody has a phone anymore. And you guys have lab partners, so at least if one of you hasn't downloaded this app, that would be great. It only does what you ask it to do. And I think that's finally what I want it to do. Okay, so jot down if you want to these titles of apps. And they're free. I went with Advanced Spectrum for the Android. I think it's Advanced Spectrum. It's Advanced something. And then just simply Spectrum for my iPad. So those are all possibilities. But again, I'm hoping that one of y'all will have it. So the lab for tomorrow looks like this. And we'll be dealing with sound. Again, there's kind of a little extra. They're fun, actually. It's like you can talk into it and you'll be like, oh, well, that's so many hertz, or give you the frequency and the wavelengths. So they're kind of fun. Let me get rid of these while I'm thinking of it. Not get rid of them. Yes. So other announcements, I guess, kind of look like this. So when we meet again in here for lecture, I'm going to have the test made out, and I'll make a review sheet that goes along with the test. And one of the things I've done for my other classes is make like a little review video, and I think I'll probably do that. Help me out for those of you who had me before in astronomy. So did you guys get credit for watching the video? No? Good era. I just watched the video and it helped. In astronomy, I made a review video. Oh, yeah. Yeah, okay. Yes. We didn't have to go that far, but anyway, yeah. So I'll probably work on something like that again. Okay, probably might not be over the weekend, but awesome. Okay, so then that means that Friday we're going to begin kind of dabbling with what we need to talk about with regard to chemistry, switching gears from physics to chemistry. One of the things who was I talking to the other day about chemistry? I just think it gets a bad rap for whatever reason. I know, and we decided that like when we're coming up through middle school, a lot of times we'll talk about the science of the weather. We don't call it science of weather, but we'll talk about the weather. And we'll talk about stars with little kids, and we'll talk about plants with little kids, but we don't talk about chemistry with little kids, and we really should. Maybe we should call it something else. Anyway, my background's in chemistry. That's why I'm a little biased about this whole thing. So Monday and Wednesday we'll also do chemistry lecture. We'll see how far we get. And then Thursday, as you know, a week from tomorrow is your first unit exam. And you will have from 10 until noon to take it. And I like to have it somewhere other than the chem lab, so you guys have like normal chairs. I'm going to bring the equation sheet, and you guys can bring 3x5, is that what I said? Index card with notes that might help you. Would you rather 4x6, a little bit bigger? Sure, let's go 4x6. A little bit bigger, that helps. So I'll pass that along to you guys, my face-to-face section, there are a few students taking it in the hybrid format, so I'll make sure everybody knows 4x6. Room to be announced. Okay? Cool. Waves, I want you to kind of No, as the sound waves, and the other one is generally what we call light waves. But both waves actually follow that equation we covered recently, where, I'll put it up here, V is equal to lambda F. So what's V? Speed, perfect. What's this one? Wavelength, and what's F? Frequency. Yep, that's it. So whether it's sound or light, it follows that, which I think is so cool because they seem so different to me. Okay. So I brought this poster to show you the whole cousin thing. Okay, because these are energies. Well, don't look; that kind of is confusing. But if you read them along the side here, we have cosmic energy or cosmic rays, gamma rays, X-rays, ultraviolet, and then light. I don't know if you can see that, but light is this much of the cousin compared to some of these others. Then we have infrared, microwaves, radio waves, ultrasonic, sonic, and low frequency. So that's kind of sort of the cousins. So here's a figure from your textbook. And again, you can kind of see that this is a little more detailed than that. But you see the gamma rays over here. Now, what does 10 to 20, what does that mean? Scientific notation, exactly. So what that means is that with regard to frequency, the cycles per second, you are talking about 1 with 20 zeros after it. That's 10 to the 20th. That's the number of cycles in 1 second that will pass one place. Okay. So what about these guys, radio waves? Do they have a higher or lower frequency? A lower frequency. Yep. So, well, over here, I'm going to say V is equal to lambda, velocity or speed is equal to the wavelength times the frequency. We said as as frequency decreases as you go from gamma rays to radio waves, frequency went down. So what does wavelength do? It's going to go up, because one of the things we're going to see with regard to velocity, how fast these things travel, all of the cousins travel at the speed of light. Speed of light. So, put another way. So these have high F, and they would have small lambda or wavelengths. These have low frequencies, and they have long wavelengths. Which one would you be, we're not a biology class, but which one would you be less worried about being hit with? Gamma rays or radio waves? I'm fine with radio waves. In fact, they're probably passing through us right now. As it turns out, these guys are low energy, and these guys are high energy. And with high energy, we can have our cells respond in crazy ways. So I'm going to go ahead and add that. So this is high energy, high E for energy, and this is low energy, low E. Cool. So it's funny, I feel like I've condensed quite a bit in these last few slides that we're going to cover for just dealing with light. And one of them is that light is what we say it travels in packets called photons. That's little photons of energy. It travels in packets. But it also travels like this. Now, of the two waves we talked about, what sort of wave is this? Is it a transverse or longitudinal? It is transverse. Transverse up and down. Longitudinal is long. Yep, long is the slinky. Okay, this transverse would be the we say perpendicular to the direction it's moving. So that's how these forms of, we call electromagnetic radiation. These are the family of electromagnetic radiation. and light is going out. Now, a cool thing, and I brought to kind of show you this. So when you buy sunglasses, sometimes you look for the fact that your sunglasses are polarized. When you polarize film like that, you're creating like a picket fence, so that will only allow one direction of these transverse waves. So the thing about polarized sunglasses is that, and I've read a little bit about it, is that they help with like glare. Like you go fishing or whatever, you're out in the river and you kind of see the glint of the, it helps to kind of reduce some of that. Okay, so if we have light doing this, okay, and we put a polarized film, only certain direction of light will get through. And so if we take two, I hope I got this right. Okay, so this you can't tell it. I'm going to kind of turn it like a magician again. Okay, I'm going to kind of turn it. A little bit. Okay, but it's not. This is one picket fence, and this is another picket fence. So if you were to take one picket fence and go this way, and another picket fence and go this way, can you see where you like play havoc with anything that wants to get through there? And so that's exactly what. Okay, so here the picket fences are going the same way. I know it looks pretty dark. Okay, picket fences going the same way. I'm going to rotate one of them. Can you see where at some point, what light is it? Well, you're like, it must be that projector. Okay. I'm going to go ahead and make my picket fences go the same way. And there you go. Isn't that cool? Then not that I encourage you to be destructive in this way, but if you take your sunglasses and it happens to break, your sunglasses have to break, you can actually do the same thing with your polarized sunglasses. Just take one lens, put it in the other one, and rotate it. And how does this work? Something about some displays, like retinal displays, like from your iPad, are polarized. And so if you've ever like tried to have sunglasses on and look at your iPad, sometimes so they're all kind of little phenomena. Cool. What else do I have? All right. So I said all those cousins. So one of the things on your note cards you're probably going to want to do, because I want to kind of make sure we're all kind of both gamma rays and radio waves and everything in between. Okay. I want you to have a sense for gamma rays have what? High frequencies, short wavelengths, high energy. Okay. And then at the other end of the, I'm not going to necessarily hold you accountable for all this, but we stop at radio waves. They have what? Long wavelengths, low frequencies, and low energy. They're so cool. And can I ask this? Well, I can ask this follow-up question. I'll go ahead and answer it. You can actually kind of go back and forth between these energies. Take the photon associated with X-rays. You can diminish the energy, and you can make it into. But light is just tiny, tiny. I guess before we leave this and kind of finish talking about the electromagnetic radiation, do you see where light on this poster, it's been broken out into the colors of the rainbow? Okay, so I know it's kind of hard to see, but see, those would be, they said these are wavelengths and angstroms. So what's the number there? Like it's 4,000. I know, I probably didn't see it. We have 4,000 angstroms, the wavelength here. Over here we have 7,500. So which one has the higher wave, the longer wavelength?
violet or red. If I said this is 4,000, this is 7,000. So red, as it turns out, has, of the colors of the rainbow, has the longest wave. And sometimes, and this doesn't have to do with the slide, but I'll tell students, it's a mnemonic device. It's like somebody's name, I don't know. And it goes like this. Their first name is Roy. Their middle name must start with the letter G because that's their middle initial. And their last name, I've heard of Roy G, but it's B-I-V, like Roy G. Biv. And I was thinking like Biv, back. Anyway, Roy G. Biv, they stand for colors of the rainbow. So what is R? Yep, red, and then O is orange, yellow, green, blue, anybody get right? Indigo, B, violet. So as I've written them, this is the longest wavelength, and this is the shortest wavelength. Roy G. Biv. And sometimes that's helpful. Actually, some of the stuff I think I was talking about physics is going to help us switch gears into chemistry and astronomy. So Roy G. Biv. Hi, now another thing I was going to bring out here. On your previous slide, what bumps up against,
What is the longer wavelength past visible light?
you see which cousin it is? Longer wavelength from visible light. Infrared. I know this is kind of backwards from that. Yep, it is infrared. Very good. The abbreviation for infrared is IR. Infrared. Infrared glasses. Okay. Actually brought a few things. Well, I don't know why I bought this, but again, it's kind of like, it's like a mood ring. You guys remember the mood rings where you wear them? Yeah. Well, of course, there's nothing here, but if I go ahead and flip it over, it will and can respond to heat. So it's totally like a mood ring. Draw on it. Okay. My point there is it's actually, you're like, well, what's it reacting with? Well, it's reacting to infrared is heat. Okay. What's a little bit shorter wavelength? This is heat. What's a little bit shorter wavelength than violet? Ultraviolet. Abbreviations for ultraviolet is UV. Of course, UV gets a rap because when we're out in the sun too long, actually that's what can mutate our cells. So we wear sunscreen. Okay. That's it. Although I did bring this. This is just one more prop. Okay, so heat is which wavelength? Infrared, yeah. So this is my little ray gun. Now, the dot actually has no significance other than to show you where the detector is pointing. So the way these work, they're so fun. They've done down the price so much. You get from Amazon, like 15 bucks. So this says 73.8 degrees, okay? So it's actually taking a thermal signature of that wall. 71.9. 93.5. That's 80 something yesterday. But anyway, so you get the idea. It's like there are things among us that we need and interact with that we just, that heat's water. So one more thing I know, boy, I hope I get through this today. I did want to have you guys listen to this video. And I just think it's E is equal to MC squared. It is the letter C. Yep. So when we say the speed of light, we should say what is the variable for the speed of electromagnetic radiation? I mean, it's all about us, but actually light is only one member of all of these things. So all of these things travel at c, the speed of light. So the speed of light rounded to, my gosh, there's 9 digits up there, but in a minute you're going to see it basically 300 million meters per second. 300,000,000,000,000 meters per second. That's how fast light travels. But that's in a vacuum. We go back to the movie Gravity, right? That's in vacuum. You think, actually, if you add any medium under the vacuum, light will travel slower. Okay. So the word medium, we talked about medium before. Sound is a medium to travel. Light can travel in space, but the vacuum space, but light, sound cannot travel in vacuum space. So here's the deal. Light slows down when it goes through air. Light slows down when it goes through glass. Light slows down the most, actually it's slipped up here, as it goes through the medium, let's see, a diamond. It slows down the most. That's kind of what makes diamonds so pretty, is it's slowing light down. Okay. There's this thing called refractive index, which is just a ratio of how light travels and how fast it goes in the vacuum divided by how fast it goes in that medium. So the bigger the number, then the slower it travels. Cool. So the thing here, when we work problems using c, the speed of light, we're going to go with this nice round number, 300 million. And the units for how fast light is traveling is going to be meters per second. Cool. All right, so we talked about this a little bit. What did I say the other day with regard to lightning? Will the light get to you first or the sound get to you first? The light gets to us first. And I know that it's not light, since it's traveling in air, is traveling slower than this, but it's pretty fast. The other day when we talked about the speed of sound, and actually in tomorrow's lab, you're going to come up with a value for the speed of sound for that particular day. It's a lot smaller than this number. So let's work a couple problems. And we'll try not to make it harder than it is. So over here I have velocity or speed is equal to wavelength times frequency. It works for sound waves and it works for electromagnetic radiation. So the numbers just get a little bit bigger with electromagnetic radiation. So it says consider red light traveling at the speed of light, and it reminds us what that is. And it says that, so I'm not going to restate this, but it says that the frequency is, T means tera, 475 terahertz. Now, one of the things you guys are running into on your homework problems is that we can't go ahead and plug terahertz into this equation for frequency. We have to get it into units of hertz. But I think I told you on your test, like I did in this problem, I'm going to tell you what the hertz are. So it won't go so much. Okay. So hertz are going to be ready to go. So let's see, there's V is equal to, so wavelength, the symbol for that, or frequency, sorry, symbol for frequency is F. So I'll put frequency is 4.75 times 10 to the 14th. I'm going to go ahead and put Hz. I could put per second also. And we're supposed to knock out wavelength. So I'll put wavelength is equal to question mark. And then up here, I'm going to put V is equal to wavelength frequency. And I'm going to divide both sides by frequency. So then that gives me wavelength is equal to the velocity divided by the frequency. The hardest thing is rearranging it sometimes. But your units should kind of show you if you got it right. So to work this, I'm going with wavelength is equal to that 300 million meters per second. And actually, in my calculator, I'm probably going to put it in scientific notation.
What is 300 million in scientific notation? Let me think. 3 times 10 to the what? I'm like an eighth, yep. 3 times 10 to the eighth. So that's what I'm putting in my calculator. Divided by frequency, which was 4.75 times 10 to the 14th. I'm going to put per second, which is what a hertz is. And when I do that, I see that my per seconds cancel. I have meters, which is awesome units. So, awesome. Okay, so what I'm looking at, I'll say the calculator value. As you guys guess, I got 6.315789 times 10 raised to the negative 7th power, and the units would be meters. Is that what you guys got? Cool. I have confirmation. Very good. Now, this is called the coefficient, this first part of the number, coefficient in scientific notation. We're gonna round that, and I'm gonna go ahead and give it 3 digits. I know it seems like I just have 1 digit here, but remember, I kind of rounded that from a 299 million, blah, blah, blah. So I'm gonna go with 3. If you went with 1 on the test, I'd be fine with that. But if I go with 3, I'm going to keep the 6, keep the 3, and the 1. What am I going to leave it a 1 or round it up? Round it up, yep. So my answer would be 6.32 times 10 to the negative 7th meters. Okay? Let's see what the next one does. Radio waves. All right. So compared to red light, our radio waves have a, it's probably up here, is the frequency higher or lower for radio waves? Lower. Yep, frequency is lower. Fewer. So is the wavelength higher or lower, or greater or smaller? Wavelength is bigger. Yep, frequency is smaller. Yep, you got it. All right, so dealing with radio waves, traveling in air, give the wavelength of, wow, that's pretty long. I mean, I could get a yardstick out. A yardstick is about a meter, so 3 yards. That's kind of interesting. So anyway, so wavelength, so that's my lambda. Wavelength is equal to 3.15 meters. Okay. I'm like, well, what? How fast is it going? What's its velocity? It's the same up here. Oops. It's 3.8 times 10, sorry, 3 times 10 to the 8th meters per second, because it's, darn it, come back. It's the speed of light. The velocity is the speed of light. Any questions about that? Okay, cool. What is the frequency? Well, if I rearrange velocity is equal to wavelength times frequency, Now, if I solve for frequency, I divide both sides by wavelength, so I get frequency is equal to velocity divided by wavelength. Are you serious? So, frequency is equal to wavelength, frequency is velocity, which is that 3 times 10 to the 8th meters per second, divided by wavelength, which is 3.15 meters. What will my units be here? Per seconds. Per seconds, yep, because the meters cancel, and I have per second in the top. So, what my calculator said, dun, dun, dun. Wow, it gave me a big number, and I'm gonna go into scientific notation. So I got 9.5238 times 10 to the 7th per second, or hertz. And if we go with, did anybody else get this? And if we go with 3 digits again, I'm going to truncate it here between the 2 and the 3, the coefficient. So we're going to leave it at a 2, we're going to mark that. So 9.52 times 10 to the 7th per second, or hertz. 9.52 times 10 to the 7th per second. Okay, so I think I don't want to rush through these last 2 slides. So I think we'll just leave it that there's nothing due on Friday, if that's okay. We'll definitely get to this assignment slide on Friday, and this will be due on Monday. But you can probably knock it away at it. I don't know if you can do it all, but okay, so we have 2 more slides and then chemistry. But tomorrow, don't forget tomorrow.